Have you ever noticed an aircraft leaking fuel right on the tarmac? A $34 million machine, and yet the engineers behind the SR-71 Blackbird did not see it as a flaw, but as a solution. Why? First, you need to understand the conditions this aircraft operated in. The SR-71, during cruise flight, heated to 316 degrees Celsius at the leading edges, a level of heat that would destroy ordinary metal. That number means nothing on its own. So imagine if you placed an aluminum pan on a red-hot burner and held it there for 3 hours. It would warp and melt. The SR-71 did not warp because it was not built from aluminum. More than 85% of the structure was titanium, a material that in the 1960s, the United States could barely produce in the required volumes. The CIA, through front companies, purchased it from the USSR, the very country this aircraft was built to spy on. But that is a separate story. What concerns us now is something else. The same titanium that saved the aircraft from thermal destruction at Mach 3 was precisely the material that made it leak on the ground. And to understand why, one assumption that seems obvious needs to be broken. Most people think of an aircraft's fuel system as simply pipes and valves, that a leak is a defect, that hermeticity is an absolute requirement that engineers either achieved or did not. But here is the problem. Materials expand when heated. This is not news. It is basic physics taught in 7th grade. But the scale of this phenomenon on the SR-71 is such that intuition breaks down completely. The titanium fuselage of the SR-71 during Mach 3 flight expanded, by various documented estimates, anywhere from 7 to 23 centimeters in length. The entire aircraft became longer, not micrometers, not millimeters. Even at the lower bound, that is the width of your fist. And this happened to every structural component simultaneously. That is how much larger the aircraft became in the air. And here the frame changes entirely. If you design the fuel sections to be airtight at room temperature, in flight when the metal has expanded, those same joints will either rupture from internal pressure or deform the structure. Take your pick of catastrophes. The SR-71 is not a defective aircraft that leaks. It is an aircraft designed to leak on the ground in order to remain intact in the sky. That is the single idea around which everything that follows is built. Now we will walk through 3 systems, each of them a proof. But the central question remains. If the engineers knew the aircraft would leak, why did they build it that way anyway? We begin with the foundation. The SR-71 did not have conventional fuel tanks in the ordinary sense, not separate containers inserted into the fuselage. The fuselage itself was the fuel tank, a so-called wet wing and wet body design. The JP-7 fuel-filled cavities directly inside the titanium skin. JP-7 is not ordinary aviation fuel. It was developed specifically for the SR-71 and had an exceptionally high flash point, 60 degrees Celsius. That means igniting JP-7 on the ground is effectively impossible. This is not gasoline. In its properties, it is closer to heavy diesel. The engineers chose it specifically because ordinary fuel at flight temperatures would simply boil and explode inside the tanks. But JP-7 combined 2 problems into one. First, it is liquid. Second, it sits inside a structure that expands by those same 23 centimeters in flight. Imagine you filled a balloon with water and put it in an oven. As the balloon warms, it expands slightly. The pressure redistributes. But if that balloon were rigid and perfectly sealed, it would simply burst. The SR-71 solved this problem radically. It made the joints between fuel sections deliberately not fully sealed at normal temperature. The gaps between panels and sections were sized so that on the ground, fuel slowly passed through them and dripped down. In flight, the metal panels heated and expanded. Those same gaps closed, sealed by their own expansion. Pilots described it as routine. Land, puddle forms, refuel, fly again. Every landing, a pool on the tarmac. Every takeoff, a dry apron once the aircraft had warmed through. But here is another fact that demolishes the most popular myth about the SR-71. Most people believe it took off with partially filled tanks, and immediately went to rendezvous with a KC-135Q because it was losing fuel through leaks and needed to top up quickly. This is not true. Pilot Richard Graham, who flew the SR-71, explains it directly. The aircraft had a technical limitation, Mach 2.6, without an inert atmosphere inside the tanks. At Mach 3, the fuel heated to over 150 degrees Celsius and the aircraft's skin to 200 degrees Celsius. The vapors above the fuel became explosive. The only way to address this was to refuel the aircraft to full capacity in the air, displacing ordinary air with fuel. After that, gaseous nitrogen maintained pressure in the tanks and prevented the vapors from igniting. The ground leak and the aerial refueling were two separate engineering problems that merely looked like one. But there is another level, and it is not in the fuel or in the titanium. It is in the engines. It breaks everything we just established. The SR-71 faced a second thermal crisis at the moment of transition into cruise flight. The Pratt & Whitney J58 engines were turbo ramjet hybrids that switched between two operating principles in mid-flight, and this meant temperatures in and around the engines fluctuated non-linearly, not a gradual warm-up, but sudden jumps. In different operating regimes, different thermal loads fell on different components. The J58 compressor blades saw temperatures where ordinary alloys would already be melting. Pratt & Whitney used nickel super alloys and an elaborate internal blade cooling system where air was pumped through microchannels inside the metal of each blade. Imagine ceramic being rapidly heated and cooled. Thermal shock shatters it. The J58 blades experienced similar stress, but the material and geometry were calculated so deformation stayed within the elastic zone, never crossing into plastic deformation. Each time, the blades returned to their original shape. JP7 served not only as fuel. In the SR-71 cooling system, fuel circulated through heat exchangers and absorbed heat from the hydraulics, the avionics, and partly from the structure itself before entering the engine. The fuel literally cooled the aircraft from the inside before burning. A third element appears that almost no one mentions. The SR-71 black paint was not only about stealth. Titanium holds its shape well when heated, but it dissipates heat poorly into the thin air at 25 kilometers altitude. So the skin was coated with a special paint containing iron particles. It radiated heat outward and reduced skin temperature by approximately 28 degrees Celsius. Three thermal management elements worked together. The paint radiated heat outward, JP7 absorbed heat inward, and the corrugated skin with its deliberate gaps compensated for expansion. None of them solved the problem alone, only all three together. But the thermal triangle solved the problem of the finished aircraft. Building it was a separate catastrophe. Titanium is a difficult material to work with in production. Welding it under normal conditions is impossible. It reacts with oxygen and nitrogen in the air, and it becomes brittle right at the weld. Lockheed had to build fully sealed workshops with an inert atmosphere, and even there the rate of defective parts shot up sharply in summer. The investigation ran for months. The answer was that technicians applied insect repellent, and trace amounts of the chemicals from their hands reached the titanium through the gloves. An entire factory rebuilt its processes because of mosquito spray. This illustrates how precisely the SR-71 demanded precision, in conditions where no engineering textbook yet had an answer. The material that saved the aircraft from Mach 3 behaved on the factory floor like a living organism with its own requirements, which is why cruise fuel consumption ran to approximately 18,000 kilograms per hour. That is more than 2 tanker trucks of fuel in 60 minutes of flight. But here is where it becomes genuinely interesting, and where most of the solutions turn out to be nothing like what you expect, because one more system remains, and it is not thermal, it is human. All the thermal engineering of the SR-71 solved one fundamental problem, preserving the structure. But inside that structure sat a pilot. The human body does not expand from heat, it dies from it. The SR-71 cockpit was insulated from the external temperature of 316 degrees Celsius asparagus by layers of insulation and a climate control system, but that system had a limit, and beyond that limit, the only thing separating the pilot from instant death was his personal pressure suit developed by the David Clark Company, the same suit used by Gemini astronauts. But the suit is not simply protection from temperature, it is a separate engineering system that solved a problem most people never even consider: pressure. At 25 kilometers altitude, atmospheric pressure is less than 4% of sea level. This is not thin air. From the standpoint of human physiology, it is effectively a vacuum. Without protection, a person's blood begins to boil, literally, not from heat, from the absence of pressure. This phenomenon is called embolism, and it develops within seconds. The David Clark suit created a sealed shell around the pilot with positive pressure, but a pressurized suit inflates. Arms, legs, torso become rigid like an inflated rubber glove. Flying in that state is like trying to write with a pencil while wearing boxing gloves, so designers wove restraint layers into the suit that preserved joint mobility despite the inflation. Even that did not solve the final problem. A pilot in a pressure suit could not eat or drink normally during flight. Missions lasted between 4 and 12 hours. The solution was a special pre-flight diet, leaving minimal residue and food tubes that could be brought to a special valve on the helmet. Steak and eggs, the standard pre-flight meal, was not a random choice. It was a protocol calculated for maximum protein and minimum waste volume over the next 8 hours inside a sealed suit. 3 levels of protection against 3 different kinds of death: temperature, pressure, physiology, and none of them intersected with what the engineers were solving on the outside. If the cockpit depressurized above 24 kilometers, the pilot had approximately 4 seconds of useful consciousness. The suit would give him time to eject, perhaps. But here is the honest part. Ejecting from the SR-71 at Mach 3 was not a scenario calculated for survival. It was calculated for the absence of a better option. The dynamic pressure at that speed would tear a human body apart before the parachute system could function. The engineers knew this, the pilots knew this, and they climbed into the cockpit anyway. This is not a protocol. It is a human decision in conditions where no engineering provides a complete answer. Over 32 years of operational flight from 1966 to 1998, not a single SR-71 was shot down by an enemy. 12 aircraft were lost in crashes, through equipment failures, and through piloting errors. Every pilot who survived those accidents did so because of the pressure suit. Those who did not survive were mostly lost because of the dynamic impact of ejecting at supersonic speeds. The fuel leaked, the engines switched between operating modes, the structure breathed, and inside, a person in a pressure suit, trusting 3,000 decisions made by Lockheed Skunk Works engineers he had never met.